All right. Thank you, everybody, for joining us for this week's HJAC. So I'll hand over.
Okay. Thank you, Catherine. So good afternoon, everyone. It's a pleasure to have all of you here this afternoon. And it is my great pleasure to introduce to you the speakers of today. She is Corinne Charbonnel from Geneva Observatory. So Corinne received her PhD in astrophysics in 1992 at the University of Toulouse in France. And thereafter, she held a number of postdoctoral positions at the Observatory of Geneva University, at the Institute for Nuclear Theory, at the University of Washington, Seattle, at the Hubble Space Science Telescope Institute in Baltimore, and closer to us at the Max Planck Institute für Astrophysik in Garching. So since 2002, she has been based at the Observatory of Geneva, where she is full professor, while also retaining a research director position of the CNRS in Toulouse in France. Since July this year, she has been promoted director of Geneva Observatory. And to add some flavor and color to such a lovely cake already, the cherry, she was in France, elevated for her efforts to promote astronomy. She was elevated to the rank of Knight of the National Order of Merit. So thank you for being here, Corinne, today. It's really a pleasure to have you here. The stage is yours. We are all looking forward to your talk. Thank you.
Thank you, Geneviève. It's good you applaud now. Okay, so it's really a pleasure to be here. I really thank Geneviève and also Catherine for helping me coming here. I have been a very bad client for her, actually answering very late, etc. But I'm very happy to be here. Believe it or not, it's the first time I'm coming to Heidelberg to do science, even though I know many people, those with the gray hair mostly in the room, actually. Anna, we were together at Space Telescope and others, so I'm very happy to see you here. I'm going to talk today about evidence of extremely massive stars. I hope I will convince you that we have evidence of extremely massive stars. I will explain you what I'm talking about in a minute. In proto-globular clusters-like conditions in the local universe and also at high redshift. And I will split my talk in 4 parts. I will first introduce to you what are globular clusters. Sometimes it looks like a very boring subject. What is a globular cluster? It's an old thing that doesn't do anything, but it has done a lot. So I will try to convince you why it's very important to look at these objects. I will discuss about their composition, the fact that they host multiple stellar population, and then I will move to extremely massive stars, which is in the mass range that you can see here between 10 to the 3 and a few 10 to the 4 solar masses. And then I will move to a new, let's say, new discoveries of very high nitrogen emitters at high redshift, and I will try to convince you that there is a connection with proto-globular clusters. So let's start with the interest of globular clusters in general. Globular clusters, they are known from the antiquity, but we had to wait for the 17th century before we could figure out that they are actually made out of individual stars. And Herschel was the first one to resolve these objects that were first called nebulae as a collection of thousands of stars. And I hope at the end of my talk you will be convinced that they are one of the most interesting objects of the universe, and that we know a little bit more than Herschel knew at that time. So what is a globular cluster? The classical definition, here you have a nice, you have a nice example of M13. So these are very compact objects with a small half-life radius, a few parsec, very bright, and in the galaxy, in the Milky Way, they are usually very old, around 12 or up to 13 gigayears. So they are actually the oldest objects in the universe that can be dated very safely. They are very dynamically stable, and they are stellar agglomerates. So indeed, individual cluster, oops, it's not mine. I have 1 hour to figure out how to use it, but it's okay. So each globular cluster is a collection of between 10 to the 5 and 10 to the 7 coeval low mass stars. Low mass stars because they are very old, so the stars that you see today are only those that have masses below 0.9 solar masses. And in the globular cluster that I will talk about today, I'm going to consider what we call type 1 globular clusters, which are globular clusters with no spread in metals. So these stars, they were formed with the same abundances, the same iron in particular. And actually, this is why you can use them you can use the color magnitude diagram actually to date them, because the stars, they were formed together. So you have this very nice way of dating clusters through the comparison between the color magnitude diagram and isochrones, for example. So they are very useful because they are an independent probe of the age of the universe, and they were used for 1 century to establish all the concept of stellar evolution. Here, in this color magnitude diagram, you see this main sequence. You have the red giant branch, and here the evolved stars that are burning helium, and here you have the white dwarf. So it was really a tool to understand how stars evolve along their life. I think for stellar physics, some unusual objects like blue stragglers, low mass X-ray binaries, etc. They are also very interesting because if you look at their kinematics in the galaxy, as is done here, maybe you don't see very well in this slide here, but you have here the trajectory of different globular clusters in blue that were actually reconstructed thanks to Gaia. And when you use that, and you also use dwarf galaxies, you are able to determine what is the mass and the shape of the Milky Way dark matter halo. So it's very important also to constrain the structure of the galaxy. They are also very important to understand how the galaxies build up. And here you have a plot where you have the energy and, oops, I'm sorry. And you have also so this is the integral of motion space, where you have a bunch of clusters here in blue that can be attributed to the original Milky Way galaxy. And when you move into this plot, you see that you have high energy clusters that can be also retrograde, that could be related, that could be attached to some different small galaxies that were accreted. So this is also something that has been done thanks to Gaia. And if you compare also the chemical properties of these clusters, you can have some information about the chemical history of the galaxy from where they are coming, and that was accreted by the Milky Way. So you can do the same thing, for example, in M31, where you see here a bunch of clusters that are associated to stellar streams that were due to recent mergers and that have not had the time to dissolve, but actually, if time passes, the globular clusters will stay solid here, and you can have some information about the history of accretion and mergers in this galaxy. So you can do that for different types of galaxy, because these clusters, they are actually very bright. So you find them very easily, and you find them in all galaxies with masses above this threshold here. And there is a very nice correlation between their number and the virial mass of the host dark matter halo. So this is, as I was saying, for the Milky Way, it's also a nice tracer of the luminous and dark matter distribution. And you can also play the same thing about the mergers history of different galaxies by looking at the number of these clusters and their distribution. So they are used as tracers of the galaxy building across time. And these observations, actually, they are nice constraints for these kind of simulations, this hydro simulation of galaxy formation, where you can also plug in the modeling of star population formation, and you can try to reconstruct the building of the globular cluster complex in one galaxy by accumulating accreted and in situ clusters. I mentioned that in the Milky Way, so the clusters are very old, and they are also very old in globular clusters in the Large Magellanic Cloud and in the local group galaxy. And overall, their formation redshift, the peak was around 7, the redshift of 7. I will manage. I told you I have 1 hour, but I will manage. And there are also some observations that these clusters have formed at a higher redshift. And this is to say also that they have been considered as very important contributors to the reionization process at high redshift. Now, I talked about old clusters, but there are also very compact and very massive star clusters that are young, that we can see in other galaxies. So here you have a collection of clusters of different masses. In blue, you have you have the galactic open clusters, and here you have, so this is the age as a function of the information about the mass, so the most massive are here. And you can see that, so these are the old one in the galaxy, and here you can see that in the small and large Magellanic Cloud, there is a bunch of clusters that formed very recently that have very similar masses to the mass of the clusters that are very old in our galaxy. And the question is, are these young massive star clusters the counterparts of the proto-globular clusters that we see in our galaxy? And so can they form, and also will they survive to their environment? Will they be dispersed in a way when they evolve a long time? So this was in the local group. Now, if we move at a very high redshift and we use the power of gravitational lensing plus GWST, we start to see very interesting objects at different redshifts. So here it's a collection of clump populations that have very small effective radii up down to 10 parsec, and masses which are very similar to the masses of the globular clusters. And this is for a collection of galaxies at different redshifts. If you move to other galaxies, like here the Sunburst galaxy, so the redshift is around 2.37. You have also a collection of clumps, and you can do the same for other galaxies. Here is it's another one which has a slightly higher redshift, and you can see beautiful, massive clumps that are also very small, very compact, and very dense with a large number of stars within. And it looks like, actually, when you look at high redshift, the star formation mostly occurs in clumps of this size and of this mass. So it looks like now at redshift above 7, etc., most of the star formation occurs in such small clumps. Here it's another one that I will discuss later. So this is kind of a summary of what I was mentioning through this observation of what was called by Angela Adamo the cosmic gems. So this is also a lens galaxy. You see the clumps here, and here is a reconstruction of their distribution. And what is important here again is to look at these bound young massive clusters that are extremely tiny but very massive. So you have really a compactness which is very similar to what we think is the compactness of the globular clusters. So today, the standard paradigm for the formation of globular cluster is that they are the natural outcome of star formation at very high redshift under very high pressure conditions. So you have very compact regions with lots of gas in a very tiny regions, and this is something that looks to be ubiquitous in a high redshift galaxy. But we still have to understand if these objects that we see now are really the progenitor of the proto-globular clusters that we see much later on in the Milky Way. And I will give you some clues at the end of my talk about why we think it's the case. So maybe I will skip this one because it takes me too far away. Okay, so this is why globular clusters might be interesting for different reasons. And now let's try to dive into more details about what are these objects. So if you look at old textbook, you will see this kind of color magnitude diagram of, so this is NGC 2808, which used to be seen as the characteristic of a single coeval stellar population born with homogeneous composition, because the color magnitude diagram is so beautiful and you have all the stars aligned, so it looks like there was no variation in abundances. But then this was confirmed also by the fact that when you look at stars in a globular cluster like this one and you make spectroscopy and you determine the metallicity, you see that there is no variation from one star to the other. So that means that the stars, they were pre-enriched, so the cluster formed out of pre-enriched material from normal galactic evolution, but there was no self-enrichment by whatever inside the cluster. But then the things changed. Yes, I'm going the right direction. The things changed when people tried to manipulate the different filters of HST, filters that are sensitive to different chemical elements. And here you see exactly the same cluster, 2808, with a combination of filters that are sensitive to nitrogen. And you see that this beautiful single population splits into different sequences where you have actually, when you move to the right, you have some nitrogen enrichment. So you start with what I will distinguish first and second population. So the first population has, in this case, nitrogen abundance, which are similar to what you would see in normal halo stars, which are not in clusters. And the second population actually is strongly enriched in nitrogen. So this was from photometry. Now, if you turn to spectroscopy and you look at different elements, so here, this is nitrogen. This is exactly the same cluster. And for some of these stars in this area, the nitrogen and the oxygen abundance have been derived. And what you see is that from this first population, which has the normal nitrogen, you move to high nitrogen into this direction. But at the same time, not only nitrogen is enhanced, but oxygen is depleted too. So you have this beautiful anti-correlation between oxygen and nitrogen. And those who do a little bit of nucleosynthesis in star, you start to see something you're familiar with, which is the CNO cycle. And again, if you look at stars in this cluster that have this strong variation if in nitrogen and oxygen, still they have the same nickel, the same iron. So there is variation of oxygen, nitrogen, but the heavier elements haven't changed from star to star. Now you can look at other elements, and here it's a collection of abundances in different galactic clusters that have different metallicity, different morphology. And what you find is what we call the oxygen-sodium anticorrelation. So here again, if we look at 2808, you have the first population here that has the same sodium and oxygen than field stars, which are surrounded here. But you see that when you move to the left, so oxygen is depleted and sodium is enriched. So the stars that are nitrogen enriched, they are also sodium enriched. And actually this anticorrelation, it has been found in all the clusters where it has been looked for. So it's an ubiquitous property of globular cluster. And now in the community, we like to say that what is a globular cluster? It's a cluster that shows the oxygen-sodium anticorrelation. It's another definition. And actually, this sodium enrichment, it has been found in the local group. So it's not only in the Milky Way, but you can find it also in other extragalactic globular clusters. Now, even more surprising, if you look at other elements like aluminium, here is again 2808. The first population is normal, and you see that the second population is strongly enriched in aluminium. And there is also a depletion of magnesium. So this aluminium enrichment you find in most of the clusters, except in the ones that have higher metallicity. And the highest depletion in magnesium you find either in the most massive cluster or in the most metal poor, like in this case. And last but not least, when you combine different filters that are sensitive to helium, now from photometry, you can see that the first population and the second population, they have also some differences in helium. So the first population would have presumably the same helium than the halo stars, normal halo stars, while the second population has some slight helium enrichment. And so in the case of 2808, which is one of the most massive clusters, this variation in helium, so Y is the mass fraction of helium, you have X plus Y plus Z, which makes 1. So here is the mass fraction, and you can see the variation between the first and the second population. But in most of the cluster, actually, there is a slight variation, but usually much less than in these very massive clusters. So the helium enhancement exists, but it's pretty small. It's not always easy to make spectroscopy in these clusters, so people had to figure out how to make some analysis from photometry to try to find out where are if you have multiple populations in different clusters. And Milone and collaborators, they had this nice idea to combine different filters. And here you have the first population and the second population, and when you compare, when you look at the spectroscopy, you see that indeed the first population, which lie here, are the ones that have the normal oxygen and sodium. And when you move here, you have the sodium enriched and oxygen depleted. So this, what they call the chromosome map, is a very powerful tool that you can use also for extragalactic globular clusters. And what you see, so here it's a collection of almost 60 globular clusters. You see very well this first and this second population separated. But when you look at different clusters, you see that it's ubiquitous, but there is a lot of variety. So there are no two clusters that behave exactly the same. The helium enrichment is higher in one and lower in the other one, the sodium enrichment. So you have this enrichment, these modifications of abundances, but to different levels depending on the cluster you're looking at. And what is very interesting is that also the fraction of the second population stars, so those that have this enrichment in sodium and depletion in oxygen, they are more numerous when you move to more massive clusters. And this is going to be a very important clue on any scenario to explain. So here you have the fraction of second population stars you see as a function of the globular cluster mass, and you see that you can go up to 80% of stars in the cluster that are second population. So that means you have a huge, you have to provide a lot of gas with this enrichment to make this second population, and this is what we call the mass budget, but I will discuss that in more detail in a moment. So the other thing which is interesting to figure out is in what type of clusters do you see these things? I said all the globulars where you look at, you find it, and this is what is shown here. So you have the relative age, and here you have the brightness of which is the proxy for the mass. Here you have an indication of the present-day stellar mass. And the clusters which are shown here, so the squares are globular clusters, and when you have colors, that means that the anticorrelation, oxygen-sodium anticorrelation has been looked for and found. So in all the cluster where it has been looked out, and it has been found. Now, if you move to less massive clusters, and in particular to open clusters, this anticorrelation has never been found. So it looks like there is a minimum present-day mass above which you see this anticorrelation and below which you don't see it. So it's like a threshold where you can make what I will try to explain to you in a moment. And the other cluster, they live their life without anything special. So of course, when we talk about present-day mass, that doesn't mean we have the initial mass, and I would encourage you to go and look at Genevieve's paper where she discussed the effect of secular evolution to try to explain how many of these first population, second population have been lost in the halo, which is also very interesting, but I won't touch that today. So there is a minimum present-day mass, like a threshold, and there is no metallicity threshold. So the globular cluster, they cover FEOH between -2 and 0, roughly. But we have seen also, so not using the exactly the same techniques, but in young globular cluster, in young massive and compact clusters with ages around 1.5 gigayear, we could find also that this second population or this multiple population were existing. So it's not a question of age or metallicity. Apparently, you can have this anticoagulation in young, but very massive cluster with low or high metallicity. But what it requires is really a special mass threshold, and a compactness condition. So you need to have something which is very compact and very massive to make the difference. Okay, so then what is the link with extremely massive stars? First, and this I borrowed to Mark Gillis, with whom I've been working a lot. Why do we try to explain all these things with extremely massive stars? Believe it, we have tried everything else, and nothing works. So you have here, this is a slide by Mark, so he compares the globular cluster expert with a cosmologist, but that could be anyone who is starting in the field. So have you tried fast rotating massive stars? Yes, we did. HEB doesn't work. Can you merge two clusters, whatever? No. So it's very simple, actually. What you need to make these abundance patterns is to have a polluter in the cluster that burns hydrogen at very high temperature. I will show you in a moment, around 70 million K. But so it burns hydrogen, makes the CNO cycle, neon, sodium, magnesium, aluminum, but it produces very little helium, which is very strange. So these are the constraints. You need to reach this high temperature, you need to produce very little helium, and you have to explain that you have so many of this second population. These are the three most important, let's say, challenges that we are facing. So in terms of nucleosynthesis, nitrogen enhancement and oxygen depletion, it's CNO cycle. Sodium enrichment is the sodium oxygen chain and magnesium aluminum chain. So this is very simple. It's hydrogen burning at different temperature. And if you want to change aluminum significantly, you need to have temperature above 40 million K. And if you want to make the anticoagulation, you have to go above 70 million K. So where can you do that? Here it's a plot that shows you the temperature on the main sequence. So each red line is the central temperature of a star of a given mass, indicated here, along the main sequence. You know that when the main sequence goes on, the core contracts, so the temperature increases. And here you have indicated the temperature that the stars can reach. So first thing to notice is that the low mass star that we are looking today, so 0.9 solar masses, they are far behind this temperature. They burn hydrogen at much lower temperatures, so they cannot make it themselves. We have also tried to see, can they make it themselves, mix a lot, and then bring this material? No, it's not possible. So that means that actually these stars, the second population stars, they were formed out of material that has been processed in a very special polluter that burns hydrogen at very high temperature. This material has been ejected, mixed with some proto-globular cluster gas, and out of this mixture you form the second population. This is the first result that we managed to have after probably 10 years of thoughts, etc. So what kind of polluters? Now, here you see that if you want to reach this very high temperature, 70 million K, you need to move dangerously to high masses. So you could say, okay, 120 solar masses could do it. But here you have the lines that indicates you the amount of helium that you have produced. And when you reach this temperature, you are at the end of the main sequence, so you have only mostly helium. So in the ejecta, you would have a lot of helium that you don't see in photometry, meaning that you cannot do it with normal massive stars. You need to reach quite high masses. And on top of that, so quite high masses where the helium enrichment is not too high when you reach this temperature. And that you can do only above a few 10 to the 3 solar masses. So that gives you important constraint. This is why we moved to these extremely massive stars. So that was There was first the idea of supermassive star that was introduced by Denis Senkoff and Herwig, and that we followed with Mark Gillis and collaborators. But then we decided, okay, let's make a separation of extremely massive star is between 10 to the 3 and 10 to the 4, and what we call supermassive stars would be higher masses. Okay, and on top of that, you need to do it whatever the metallicity. So it cannot be POP3 stars. You cannot form in metal-free environment a POP3 massive star that would make it, and then you would have the enrichment, because you need to do it at every metallicity. So it has to be something different. And you need to produce this large amount of second population. So you need to have a star that not only produces this material, but does it in very large quantity. And this is what we call the conveyor belt, which I will explain in a moment. Okay, so there are different ways of forming very massive or extremely massive stars. You can do it by gas accretion, and if you extrapolate what is called the inertial inflow model of massive star formation, which I won't enter into details, you can actually form very massive stars with masses that are related to the mass of the cluster, and you can see from this line that you can go to very high masses if you are in a very massive molecular cloud. Another way to form extremely massive star is you need to have the same kind of context, so a large molecular cloud. But if this cloud is still accreting gas, you might actually at some point, so the cluster will contract, you will reach a certain density where you can start to have runaway collisions. So if your cluster becomes very compact, the stars that are forming, they are actually collisioning. And through this runaway collision, you can form extremely massive stars. And I will show you some results of this calculation. So probably we are in between these different scenarios. You need gas accretion and you probably need collisions. And in both cases, you have to be in very compact regions. So back to what we were seeing at high redshift, and this idea also of a compactness or a mass threshold to make it happen. Because you won't have runaway stellar collisions in a loose cluster, for example. You really need to be above a certain compactness. So this is what I will show in these very simple figures here. You have the evolution. So imagine you have a cluster that forms a certain number of stars with the numbers indicated here. And all these stars, they are accreting gas. The cluster is accreting gas. And you can see how the total mass in the stars is increasing here. And as a result of this, you will have the radius of the cluster, which will shrink actually. This is what happens here. So for the different initial number of stars, you will have a shrinking of the cluster where you can start to have these runaway collisions. And this is what makes you, at a certain time, forming extremely massive stars just through these collisions. And here you can see that the maximum stellar mass of what I call the target. So here in this calculation, we imagine that there is only one target which is collisioning with the others, but that was a preliminary attempt. But you can see different things. First is that if you have too few stars, actually, you never reach this runaway configuration, so you will never produce very extremely massive stars. And you need to have something above a few 10 to the 5 stars to make it happen. And you see here in this context, you have this number. So this is the maximum mass you can get in this when you have this initial number of stars. And you can see you can go to very high stellar masses depending on when you start from. So this scenario seems to be interesting, even though it's not final and it's not very complete, etc. But it has a connection with the observation in the sense that you need to have an initial number of stars and an initial compactness in order to make it. And this relates to what we were seeing actually, that the second population or this multiple population, they form only above a certain mass, and the cluster in this case doesn't care about the metallicity. Actually, it can happen whatever the metallicity, as long as you have this compactness and this accretion. The other thing which is interesting is that the more massive the cluster, the more massive the star. And actually, if you go to more massive star, you will reach higher temperature, so you will be able to deplete magnesium more efficiently. And this relates to the fact that it's in the most massive clusters that you have the most massive stars that make this magnesium-aluminum anticorrelation. So it goes into the right direction. Another important thing is that in this model, actually, we took into account the fact that not only the stars collide and the mass grow, but we took also into account the winds. And actually, there is a certain configuration where you can have, so the target is continuously accreting some gas and some other stars. So its mass is increasing, but it also loses mass, and you can process much more material than the actual mass of the star. So the total amount of the material that you can process in this nuclear reactor can be more than 10 times the actual maximum mass of the cluster. So this is what we see here, where you have the amount of material processed, and actually through this kind of simulation, you can process up to half of the mass of the cluster through this hot hydrogen burning. So this is also aligned with the observation that the more massive, the more massive the cluster, the more you process the material, so the more material you have to form the second population. So it fits also this observation. In this calculation, we had not taken into account the mass loss that can be induced by collisions. So it's something that we looked at recently, and it's the work of Jaime Roman Garza, who is PhD with me currently, and he has done the hydro simulation of extremely massive stars that are engulfing stars of different masses. Here you have the amount of material which is ejected by 100 solar mass at each collision, and depending on the companion mass, or the mass of the star that is going into collisions, you can lose very high amount of material at each collision. So it's also something that has to be accounted for in the simulation, not only the wind. And when you do that, actually, you can reach some conversions where you make a conveyor belt star that has a given mass here, and that loses a lot of material through winds and collisions, and also which stays at a constant mass. And through this, you process a lot of material for quite some time during the evolution of the cluster. And when you do that, the good thing is that you bring fresh material to your conveyor belt all the time. So the actual abundance of helium stays very small. This is what you see here. So when you keep accreting, the amount of helium stays very small, and this is also in agreement with what you see in the second population, that there is enrichment in hydrogen burning products, but very little enrichment in helium. So not only you need an extremely massive star that burns hydrogen at this temperature, but you need this star to make it for quite some time, and that processes a lot of material, much more than its actual total mass or maximum mass. So maybe I will also skip this one. So let's take let's see now how we can reproduce the abundances. So here you have oxygen and sodium and nitrogen here for 3,000 solar mass stars. So here you have different metallicities, which are indicated by the different colors. And you see the star shows you what is the actual composition of the ejecta of the supermassive star. So you have very strong oxygen depletion, and this oxygen depletion is stronger in the lower metallicity, which is in agreement with the observation. And here you have the initial composition, which is shown here, and the curve that I'm showing here is what we call the dilution curve. So we expect that the first population would be born with these abundances. The ejecta of the extremely massive stars is here, and actually the second population would form out of dilution mixed of this material ejected by the extremely massive star and the initial composition. So you will actually populate this dilution curve with second population stars. And so here is an animation that shows you that the effect of mass, so the more massive star, the higher you go into this direction, so the more oxygen you deplete, and also the more nitrogen you produce. But in the case of sodium, actually, you start also to increase the sodium abundance when you go to more massive stars, but then you also decrease it. So looking at these kind of simulations and comparing with the observations in different clusters, you can have an idea of what was the actual mass of the star that has polluted the cluster to make the second population. So this is a way to make it. We are far from the end of the story, but at least we have a scheme. And one thing which is also probably very important to take into account is the fact that probably there is not only one target. So here I mentioned one star which is collisioning with all the other ones, but probably in this kind of configuration, any kind of star could collide with others. So you will probably have very massive stars, and we start to see in some of these extremely compact clusters also some very nice indication of very massive stars. So it's an indication that in this configuration, you change the initial mass function quite significantly. Okay, I don't know how I'm doing on time. Okay, so I will move to the last part, which is about these nitrogen emitters, and try to convince you that maybe at high redshift what we see are the proto-globular clusters. So it was a surprise from Webb that some very high redshift galaxies were found to have a very peculiar UV spectrum. And here in particular, you have these very strong nitrogen 3 and nitrogen 4 lines, which were used to determine the nitrogen abundances of these objects. And here, this is GNZ11, so 11, the redshift is 11. It's a very, very compact object, and probably it hosts at least one very, very compact proto-star cluster, and maybe several. What is very extraordinary, so I mentioned very strong nitrogen enrichment, is the following. So I will take some time to explain this figure. So here you have nitrogen over oxygen of GNZ11, which is here. Here you have the metallicity for extragalactic people, it's oxygen. And here you have a comparison with H2 regions in different galaxies. You see that this kind of nitrogen or nitrogen over O enrichment had never been found before. All the other galaxies actually were found to follow this very nice line here. And there is another important element, which is that carbon and oxygen were also determined. So in the case of GNZ11, there were big error bars, but you will see in other ones that it's more interesting. So, you know, it's the story of the hammer and the nail. If you have a hammer, you think everything looks like a nail, but we did the same for this GNZ11. We were thinking about globular clusters, so we compared the abundances, so the nitrogen over oxygen in nitrogen 11, which is here in yellow. And we compared to, so these are the same H2 regions that I was showing before. So this would be the first population, so normal galactic evolution. And here you have the N over O in a number of clusters, so 6397 globular, this case, 47 Turk and other globular clusters. And you see that they all start in this area, first population, and they climb this line here. So the second population are here. And of course, the reaction was to say, okay, GNZ11 must be like a globular cluster because it lies in this area. So there has been a lot of studies about that, lots of papers. It's very difficult to quote all of them. But here you can compare also what I was showing before. So these are these dilution curves that I was showing before, but now for N over oxygen. This is the ejecta of the extremely massive stars at different metallicity. And here is a dilution curve. And you see that we can explain GNZ11 with the same dilution curve that we would explain this 2808 actually for second population. So it looks like this very compact, extremely high redshift object could well be hosting a supermassive star, which is presently polluting its environment, hence a proto-globular cluster. So there was a lot of excitement in the community. I think probably 15 papers came out in 3 months about this thing. And of course, the question is it unique? So there were now several of these nitrogen emitters that were found. Here is CS1019, also very strong nitrogen lines here. It's also a high redshift star-forming galaxy. You can see here actually it can be resolved in 3 clumps that have quite small radii but very high masses. So again, extremely compact star-forming objects. Here is another one at redshift 9.4. And if we could keep going, so this was a summary. Now there are even more. It's a paper from Daniel Ferrer last year, where you have a comparison of the position of these nitrogen emitters, now in nitrogen over oxygen and carbon over oxygen, compare again to this H2 region. And you see that objects, they are really standing out in nitrogen. Another thing they are standing out is their compactness. They are also this nitrogen enrichment compared to the other H2 regions, galaxies, is that they are really at the end of this figure here, which is the highest stellar mass and SFR surface density. So again, connecting compactness to the presence of this very high nitrogen enrichment is quite promising. And I show you again this plot so that you can compare the theoretical lines, these dilution lines, with the observations here. And the good thing is that with these extremely massive stars, we don't make too much carbon, so this is why we can explain them. There were several propositions of other objects where the carbon and oxygen could not be explained, and we think it's very promising. Since I'm a bit late, I will move to that. So that could be a proto-globular cluster hosting extremely massive stars, but that could also be eventually a very brief phase of the evolution of a normal galaxy. So we tested that. This is the evolution with time of the abundances of different elements, considering the yield for stars over a broad range of masses. Here you have the masses of the stars that die at different times, so you can figure out when they come into the scene. And we have considered stars with and without, models with and without rotation. And what you can, so here in yellow you have the GNZ11. So you can see that there is indeed a very brief moment in this normal galactic chemical evolution where you can make when you can explain the observations, but it comes also at a moment where you have very strong helium enrichment. So that means if it's the case, it cannot be a proto-globular cluster. It can be a phase of the evolution of the galaxy, but this region will not be a globular cluster because you already have too much helium enrichment. And if you move on with time, you have the helium burning products that start to appear. So you have a strong increase of carbon. So you move away from these observations, actually. And so again, that's a very, very brief phase before you bring the fresh helium burning products from this massive star. So it can be this, but in this case, we are not looking at a proto-globular cluster. So there are probably a few of these nitrogen emitters that are indeed transiting through this phase. These are nitrogen emitters where there has been some signature of Wolf-Rayet stars that you can see here. There are a few of them, I think 3 or 4 of these nitrogen emitters where Wolf-Rayet signature have been found, and this could well be during this phase. So we don't say it's black or white. It could be a mixture of these different possibilities, but probably statistics will make it more clear. So I hope it could be proto-globular clusters because the conditions are really what we expect in terms of compactness. And as I was showing you also in this length galaxy, we have the very nice conditions to form these objects. But okay, who knows? It could be also a rare phase of the evolution, and probably statistics will help us into this. There have been also other propositions for crystals, but in all these cases, all the other cases, it cannot be proto-globular clusters, because what you would have had after some time in their evolution would not look like the globular clusters that we have today. So we'll see from statistics and probably more surprises in the future what is happening. But so I think it's time for me to resume. So I hope that I convinced you that globular clusters, they are very useful in astrophysics and cosmology. They all and only globular cluster host multiple stellar populations that have very unique patterns. So that can be a definition of a globular cluster. This requires hot hydrogen burning in extreme objects that are not producing a lot of helium, or which produce some helium, but when they are not furnished anymore in collisions or through accretion gas, probably at the end, when they stop accreting gas, etc., they will live their normal life and they will produce a little bit of helium. But the amount of material that you release at that time will be very small compared to the amount of material that they will have released during this conveyor belt phase. And it looks like we have the conditions at high redshift to connect what we see now in this old globular cluster to what we see in high redshift galaxies, where it looks like these high pressure compactness conditions are actually forming at least doing one third of the star formation. And so are these nitrogen emitters that have these nitrogen properties, are these the proto-globular clusters? Let's see. If there are, so that means that we have seen the first in nature of extremely massive stars in the universe. And I will conclude just by asking you, are you like Herschel? Do you find that these objects, well, we know a little bit more than Herschel knew, but we were talking with Nadine earlier today, and the more we have observations, the more we think we know, and the more confusing it is. But I hope you are convinced that they are among the most interesting objects in the heavens. And with this, I will conclude and be happy to take your questions. Thank you.
Thank you for this talk. So I'll open the floor for questions, particularly from students and postdocs. Don't be shy. Don't be shy.
We stay students all our life.
Let's see a hand.
So, hi, very nice talk. So I have a question about this dilution fraction in your models. And it seems like a free parameter. But I wonder what is the physics behind this? Like what physics really determine this fraction in reality?
Okay, so probably this, so maybe if I come back into this, yes, this one here on the left. So it's really schematic. Let's imagine you have only one polluter. You have stars which are still forming. So what I didn't say is that we make the hypothesis that we have a certain number of stars, but actually with a peak in the IMF, which is much lower than the normal peak, so they are accreting. And you know that to form low mass stars, as the one we see today, you need something like 15 million years, something like that. And the stars, they are not static, so they will also, so there will be probably some boundary accretion and different aspects. So this dilution will be related to where the material is ejected compared to the orbit of your object and how many times you will go through this pocket. So
I see.
it's part of the physics. So I'm going to tell you a secret, but don't say it to anyone. This paper, I call it privately the miracle paper, because at each step, so when we try to explain things, a miracle occurs. Okay? So I think the first miracle is that it's normal. If you have a cluster with stars that are forming, you accrete a lot of material, it's normal that you change the potential, well, it's going to shrink and you will have collisions. Okay? That's the first miracle, but it's easy to understand. Then you have to expel this material with the right composition. Second miracle, you can do it with extremely massive stars that maybe we have seen in this nitrogen emitter. Then the other miracle that nobody has really tried to touch is how you form this second population, really. So I tell you the big ideas that we have, that you might have these things. So this dilution is that you still accrete some gas, which has the original composition. And you have all these things mixing together, the ejecta. So this is what we have behind this name of dilution. And so the stars which are close from the first population, they will be made mostly of this original gas. And then the more chances you have to accrete or to get this material closer from the extremely massive star, the more extreme you will be in the second population.
So are there people trying to simulate this process with the best codes we have? Because it's in principle we can simulate this, but of course there are limitations in resolution and other things. Yeah.
Well, there are people with whom I'm talking. Well, here is Ralph. There are people like Patrick and Bell, etc. But you need. I mean, Ralph, you can say better than me about this star formation in all these conditions. It's extremely complicated. But I would be happy to have also your comment on this. Would that be feasible? And when I don't know the answer, I put the microphone.
Okay, that comes as a surprise, but thanks for this fantastic overview of the miracles of globular clusters and the enigmas that they offer. So, I mean, Bojan, you know, just in a sense as well as me, that there are so many pathways to make these very dense configurations in the centers of galaxies, in high redshift halos where you have these huge accretion flows. You have puffy stars because they accrete, they have larger radii that increases their encounter and collision probability. If you have just some binaries, that also will increase the collision probability. And so I think to have conditions where you have runaway collisional mass growth is not something completely out of the picture. I think actually in dense environments, it's a very natural byproduct of the environmental conditions. And I think people who then, like Michela, look at stellar collisions can also say much about what the outcome of these processes is. I also have a question, I don't know, but I'm not... All right, I take the advantage of having these things. So this is all great, and I like the runaway collisional mass growth and all the dynamics that comes along. But I'm still wondering whether we maybe do injustice to stellar evolution if we talk about binaries and triple systems, right? Where you have upwelling, where you have maybe the stripping of envelopes, where you have all kind of things that can also produce weird abundances. And so I was just wondering, is this something you would still consider, or what is your opinion on
normal
that?
stars in binary or triple systems?
Well, but I mean, if you have compact binaries, right, you have all kind of mass transfer, you have upwelling, you have meridional circulation. You can rejuvenate the star and do all kind of things. Wouldn't that help in many ways?
No, that would help. Sure. Actually, the collisions, all these things will help.
Yes.
And yeah, we have even more parameters. Now, people have looked at the effects of binaries. Intermediate mass binaries are between 10 and 20 solar masses to try to improve the question of the mass budget. But there are two aspects with that. First is that you don't reach the high temperature. So if the collisions make for a moment the star hotter, and you can burn, etc., so that would be something maybe to try to figure out. We even thought about a white dwarf that would go through, you have accretion, it would increase the temperature. But there is the question of the mass budget. So you really have to have a lot of material coming out of these polluters. And so far, even though it's again a miracle that you have this conveyor belt, in order to have 10 times more than the maximum mass of the star, you really need to have something, or you bias. So we also looked at the effect of having a normal initial mass fraction independently of the helium stuff. To say, okay, if we have a normal IMF, we form a little bit of this hot hydrogen burning from normal massive stars. We put it in the cluster, we form just a little bit, a small number of second population, and then we throw away all the first population. That would be a way to reverse this mass problem. So you lose all the first population, and this is why at the end you have this fraction that we have now. This is very, very robust also, this, how you can eject, and also it's something that Genevieve, I think, is looking at, how you can eject, how you eject the population. When you eject the gas, you need something extremely violent to make it happen. So it's also something that has been looked at. But what made us change really the paradigm to the extremely massive star was this helium variation, which exists, but which is extremely small. If you do with normal massive stars, you will reach this temperature, but when you have a lot of helium. And then, so unless the helium variation is much more than what photometrists tell us is. But if you have this very small helium variation and a lot of material to produce, the only way is to refurnish all the time the nuclear reactor and to process a lot of material. I don't say it's happening, I just say from the Nucleosynthesis point of view, helium was really the key, was the killer of all the rest.
So while you are showing this slide, if I understand it correctly, you could, in principle, if you compare this with the observed abundances of second population stars in real globular clusters, you could reconstruct for each of these stars in a given globular cluster what the mass of the progenitor star was, right? So can you, from that, derive an initial mass function?
Well, in principle, we could do that. Because we know what is the present day mass of the cluster, but then you have also to go back to the initial mass of the cluster and how many of the first and second population have you lost. For the, okay. Yes, so it's true. So the more extreme they are, the more massive the star has to be, or the more metal poor it has to be. So you also have, so if you know the metallicity of the cluster is okay, so you have an indication about the mass of the star. But the dilution is also something, so you could have something even more extreme. And the dilution would be stronger. So yes. We can play with that. It's difficult to have, let's say, one model per cluster and to be sure about that. The trend is that the more massive the cluster, the more massive star you can form. This is correct. And the more massive the cluster, the more you can process through these extremely massive stars. So that goes into the direction of explaining the mass budget, the amount, the fraction of second population. But these are directions. Now, to be very precise, what would be exactly the mass? One thing which is interesting, I think, is that the magnesium-aluminum anticoagulation you don't see in all the clusters. And so that tells you that you don't need 10 to the 4-ish solar mass stars in all the clusters. But where you see this magnesium depletion, then you need to go to very higher masses. Yeah.
Another question.
So fantastic talk, and I find this scenario totally convincing. But coming back to the helium, to the problem of the helium, because I think this is really the delicate thing. It seems maybe problem of fine tuning even for the very massive star or supermassive star, because I mean. If the collision product rotates, you can have a chemically homogeneous evolution, and that also allows to eject helium. And in general, the collisions spin up the collision products, so this also goes into the direction of mixing the star and ejecting helium. So it seems quite difficult to me that you can keep the fraction of reprocessed helium low, even in the scenario of the extremely massive star.
No, yeah, that's true. Now we need to make these models of what I showed about the mass loss from the collisions. Actually, we have this hydro simulation where we can follow the readjustment of the structure of the star, and it starts pulsating also. So we also have some indication of these pulsations where you will have. But we can't go very far in these simulations, and so, yes, it's open to new discoveries, I think. So again, it's a miracle. It's idealized way of processing a lot of material without producing a lot of image.
Maybe one last question.
Okay, thanks a lot for a great overview. One comment to Mikila. One thing I could think about is if the helium, you could think of decoupling at low metallicity, but on the other hand, you probably need mass loss rates that are so high that you don't really have radiative decoupling then happening. I didn't see an HRD, maybe I missed it, but I was wondering what would be the temperatures of these stars and what would that mean for the signatures? Because if you say it cannot be the Wolf-Rayet signatures, then are there any other signatures one should look for even in nearby galaxies? Because if this can happen to relatively high metallicities, then in principle there's nothing that should prevent us from seeing this in nearby star-forming galaxies, right?
Yes. So I will show you a color magnitude diagram, and you will understand why I didn't show it. Be around here. I'm sorry, huh? Oh, sorry about that. Thought I would have it. So, okay. I have it somewhere. Maybe I show it about. Okay. So, because you have very strong accretion, the star is inflated a lot. So the temperature is around 5,000 K. And it's extremely bright. And we had some modeling of atmosphere by Fabrice Martins, who showed that there could be some signatures that we could see in some cluster, and it was the work of Adarsh Puruvandoti, who looked at these signatures in a survey of young massive star clusters, the name of which is going to come to my mind very soon. But they were never in this survey, they were not compact enough cluster where we could see it, which may be fortunate because otherwise, okay. So there could be this possibility that you have this very specific signature, and I can show you which papers. Now, one thing is that we don't know how the convection works in these objects. So we have this poor MLT modeling of convection. And if we change a little bit that, and there are some tricks to change it a little bit, so to make the energy, to make the evacuation of energy more efficient, the star can be totally blue. So depending on how you treat the convection, it can be very red, very cool, or it can be very hot. So from the stellar point of view, I don't feel very comfortable. What am I doing? Okay, I'm happy to say they are accreting a lot, but depending on how you treat the expulsion of energy through convection, you can have anything. So it's another problem. But I will find it. I will show you after the talk if you want.
So before we thank our speaker again, I'll just announce that there will be dinner with the speaker, and there's still a few spots free. If you're interested in joining, just come on down here to the front. So thank you again for this.
Thank you.
Talk.